Hello and welcome to the parallel programming. So, like we were discussing, in this session we are going to introduce ourselves with the basic parallel programming algorithm. So, as the most programming language start, we'll also start with our Hello World program. So, which we have ready over here. So, let's introduce first of all what is the essential, which is a requirement, and what needs to be done. So if you see the stdio, string, these are like common libraries. But what we see over here, the new library is a hip runtime. So this is the required library which defines all the global kernel functions, keywords for the hip programming. So when you want to write your parallel programming with the hip, you need to make sure that you are having this hip runtime library. And that's what comes with the rocm software stacks, what we have installed, so that we are able to execute this successfully and we can run it. So now what? So now what comes next is like usually you would have seen in the C function that we can define a function with the return type and the function name. But there is an additional keyword which is coming into play here. So this global keyword, it means that this function is a shared by both CPU, which is known as a host, and the device, which is a GPU. So both host and the GPU can access this kernel call. Okay, so that's what it means. So basically both have a access to the signature. Now there is the print function only we are writing over here that will write from the GPU. And what you see over here is a thread ID and a block ID from the grid X. Okay, and this is what we will be getting only if we have the valid hip runtime environment, because this is a keyword defined into the hip runtime. Then comes our main function where we'll try to invoke the function. So we simply have defined this heap error signature as the heap calls, for example, this heap get last error or device synchronize functions. It has a return type of a heap error. So which is why we are also trying to use this feature. And what we are trying to do over here is just halting our code execution so we can properly trace it that what has been happening. And then we have our kernel call. So if you notice that three angle braces which are used as a kernel invocation function, where this first line mentions that the number of blocks we need to initialize, and this mentions that number of threads we need to be initialized when launching this kernel. So the size of the maximum number of block and a maximum number of thread, it depends on the every hardware to hardware. So if you try to get a maximum than that, then you will see the bottlenecking of performance. And if it is fitting, then there won't be any bottleneck issues. Currently, we have this on a comment, so we would be able to see that why it is needed. So we'll come to that later on the first after the first execution of the code. And this is to capture any kind of error which would have been occurred into like our kernel execution or any other heap runtime call. And once we'll complete the execution, it is just tells that GPU execution complete and the CPU execution complete, and we need to halt once again. So before printing the hello world from city, we are again like pausing our code base. So now let's see what has been happening and why the device synchronize is important. So when we want to compile the hip code, you just need to do it right is I have this directory and this hello worlds.cpp, and there is a compiler which is a hipcc, so which is GCC plus hip runtime environment compilation. So you can see that into the hipcc we have a C compiler, but it compiles with the hip runtime, and it has all the library path it is aware of. And this hipcc again, it comes with the rocm stack which would have been installed. So we have this hipcc, and in the hipcc we can just run simply hipcc our input file, which is a hello world.cpp, our output file name say hello world dot only hello world. Okay, and we can just execute our hello world. So we can see now that first that we have our executable ready and we can execute it. So we are right now halting before the kernel launch. So currently no kernel has been launched. So when you press enter, so now you see what has been happened. So if you notice that we call this GPU kernel invoke first. But if you see that this GPU execution complete has been printed first. So what has been happened is that we have launched our kernel, and by the time that GPUs start prints this on the console, our this command line, our CPU execution is still continuing, and it collects the next line of the execution on the console and it starts printing it. So we have this line printed, this line also printed, and we are giving halt again, and then comes the hello world from the CPU. Now, if we want to prevent this kind of issues, for that only we have this hip device synchronize. So it acts as a barrier. And again, if you don't know what is the concept of the barrier, then you can check out the link again in this session to refer what is a barrier in the parallel programming. So we are going to add a barrier over here. So once we add the barrier, it will make sure that all the GPU execution has completed before we carry forward with the CPU execution and end our program. So now let's see over recompile our source code. So we have recompiled the source code over here. We are trying to run again now and again halting. Now this time I print enter, and because of this hip device synchronize, it has executed all the GPU thread, which is a 4 thread in each block, and then it printed GPU execution complete and now halting for CPU execution, and once I hit enter, it prints the hello world for the CPU. So I know this is not needed for CPU execution. Now what next? Like, okay, you see that this is running on the GPU because of a heap runtime environment. But there is a difference also that you can measure. Like you can see that whether this code is actually running or not and what impact it brings on our GPU execution. So let's say that in this program, we will keep monitoring with the amd-smi monitor VRAM usage. So what we will expect is that we will see the variance in the VRAM usage. Now there is a Linux utility called as a watch command and -n 0.1. So if I add a 0.1, every 0.1 second, it is refreshing the results, what we are executing. So now this data we have in the parallel. So now when I run this hello world program, and when I'm executing. So if you notice, there is a spike in our VRAM usage. And as soon as I'm quitting the program, you see that spike has been gone. So that was the usage that we noticed, which is happening inside the GPU. And since we don't have a large enough calculation, if we even try to measure the GFX usage, it may not reflect as a significant. So we can still have it to showcase. So now we are supposed to expect that we are having a GFX utilization, memory utilization. But when we'll actually come over here in the usage, so currently our usage is so lower that we won't be see a significant spike, as you can see over here. If we see that there is a VRAM spike, but it is so small compared to this 190 GB of a gigantic memory. So we are not seeing the percentage spike up. So that's what. So now what we will do. So now you see this GFX clock. This is something which is different. So now GPU is idle, no instruction in its streaming multiprocessor, no wavefront, anything. So it is now again it sets a bare minimal clock rate. And since we are measuring at every 0.1 second, we are seeing this kind of clock rate fluctuation, which would likely to happen. So it doesn't mean that we are trying to using it, because if you notice that when we are using it, we will see significant spike into the clock rate. like this. So see, the clock rate has increased about like 2000 megahertz. Okay, so that's what it's about our execution. And that's how we'll know that our code is actually being executed. So congratulations and hooray. So because we are successfully able to run our first Hello World program, and we now know that how to launch the kernel for a parallel program with like any number of blocks and threads that we want for our system. Okay, thanks again for joining into the session, and please like, share, and subscribe.